experience that all intuitions about what nature's going to do philosophically fail. It never works. One just has to work out all the possibilities and just try all the alternatives. Now, in this particular case that I'm talking about here, these theories are exactly equivalent. The mathematical consequences in every one of the different formulations of the three formulations, Newton's laws, the local field method, and this minimum principle, give exactly the same consequences. What do we do then? You will read in all the books that we therefore cannot decide scientifically on one or the other. That's true. They're not equivalent. They are equivalent. Scientifically, it is impossible to make a decision. Because there's no experimental way to distinguish if all the consequences are the same. Psychologically, they're very different in two ways. First, philosophically, you like them or don't like them. Training is the only thing you can do to beat that disease. Second, psychologically, they're different because they're completely unequivalent when you go to guess at a new law. As long as a physics is incomplete and we're trying to find out the other laws and to understand the other laws, then the different possible formulations give clues as to what might happen in other circumstances. And they become not equivalent in psychologically suggesting to us the guess as to what the laws might look like in a wider situation. For instance, Einstein noticed that the law of gravity, he said that he realized that signals couldn't propagate faster than the speed of light, for electricity. He guessed that it was a general principle, the same guessing game as taking this angular momentum and extending it from one case where you proved it to the rest of the universe. He guessed that it was true of everything, and he guessed that it would be true of gravitation. If the signals can't go any faster than the speed of light, it turns out that the method of describing the forces instantaneously is very poor. And in the Einstein generalization of gravitation, this method of describing physics is hopelessly inadequate and enormously complicated. Whereas this one is neat and simple, and so is this one. So we haven't decided between those two yet. In fact, it turns out that the quantum mechanics says that, and exactly as I stated them, neither is right, but that the fact that a minimum principle exists turns out to be a consequence of the fact that on a small scale, particles obey quantum mechanics. And the fact is the best laws at present understood is really a combination of the two, in which we use minimum principles plus local laws. And the present day believes that the laws of physics have to have the local character and also the minimum principle. But we don't really know. So, it's this way, that if you have a structure that's only partly accurate and something is going to fail, if you write it with just the right axioms, maybe only one axiom fails and the rest remains. Just change one little thing. But if you write it with another set of axioms, they all collapse because they all lean on that. But we can't tell ahead of time, without some intuition and guesswork, as to which is the best way to write it until we find out the new situation. So we must therefore always keep all of the alternative ways of looking at the thing in our heads. So the physicists do Babylonian mathematics and pay little attention to the precise reasoning from fixed axioms. One of the amazing characteristics of nature is this variety of interpretational schemes which is possible. It turns out that it's only possible because the laws are just so unspecial and delicate. For instance, that the law is the inverse square is what permits it to become local. If it were the inverse cube, it couldn't be done this way. That the other end of the equation, that the force is related to the rate of change of the velocity, that's a consequence that permits this kind of a way of writing the laws, the minimum principle, because if, for instance, if the force were proportional to the rate of change of position instead of velocity, you couldn't write it in that way. If you try to modify the laws much, you find you can only write them in very much fewer ways. I always find that mysterious, and I don't understand the reason why it is that the laws of physics always seem to be possible to be expressed in such a tremendous variety of ways. They seem to be able to get through several wickets at the same time. Now I would like to make a number of remarks on the relation of mathematics and physics, which are a little more general. The first is that the mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now, I explain that. If you state the axioms, you say, such and such a so, and such a so, and such a so, what then? Then the logic can be carried out without knowing what the such and such words mean. That is, if the statements about the axioms are true, are carefully formulated and complete enough, it is not necessary for the man who's doing the reasoning to have any knowledge of the meaning of these words, and he'll be able to deduce in the same language new conclusions. If I use the word triangle in one of the axioms, there'd be some statement about triangles in the conclusion, whereas the man who's doing the reasoning might not know what the triangle is. But then I can read his thing back and say, oh, a triangle, that's just a three-sided what have you, that's a so-and-so. And so I know this new fact. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. It's necessary to, at the end, to translate what you figured out into English, into the world, into the blocks of copper and glass that you're going to do the experiments with to find out whether the consequences are true. And this is a problem which is not a problem of mathematics at all. I've already mentioned one other relationship that, of course, it's obvious how the mathematical reasonings which have been developed are of great power and use for physicists. On the other hand, sometimes the physicist's reasoning is useful for mathematicians. Mathematicians also like to make their reasoning as general as possible. If you say, I have a three-dimensional space, ordinary space, I want to talk about ordinary space. You know, you're in it and you measure distances and there are three numbers you need to tell where something is. You go breadth, width, and height, three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. Now, the physicist is always interested in the special case. He's never interested in the general case. He's talking about something. He's not talking abstractly about anything. He knows what he's talking about. He wants to discuss the gravity law. He doesn't want the arbitrary force case. He wants the gravity law. And so there's a certain amount of reducing because the mathematicians have prepared these things for a wide range of problems, which is very useful. And later on, it always turns out that the poor physicist has to come back and says, excuse me, when you wanted to tell me about the 4 dimensions. Now, another item that's interesting in this relationship is the question of how to do new physics. Is it important to have a feeling, a kind of I must mention one other item. When you know what it is you're talking about, that these things are forces, and these are masses, and this is inertia, and this is so on, then you can use an awful lot of common sense, seat-of-the-pants feeling about the world. You've seen various things. You know more or less how the phenomenon is going to behave. Well, the poor mathematician, he translates it into equations, and the symbols don't mean anything to him, and he has no guide but precise mathematical rigor and care in the argument. Whereas a physicist who knows more or less how the answer is going to come out can sort of guess part way and go right along rather rapidly. The mathematical rigor of great precision is not very useful in the physics, nor is the modern attitude in mathematics to look at axioms. Now, mathematicians can do what they want to do. One should not criticize them because they are not slaves to physics. It is not necessary that just because this will be useful to you, they have to do it that way. They can do what they will. It's their own job. And if you want something else, then you work it out yourself. The next point